Hello. Let's go ahead and get started today. It's your host, the Elevated Engineer. Today we're doing something new. We're going to do a live Kaggle competition that I am participating in, and I actually will be submitting this competition today, May 31st. So I just wanted to go over some of the stuff I've been doing. I don't really know how long this stream is going to last tonight, but we're going ahead and get started. Hello, everybody. I'm the Elevated Engineer. I hope you guys like some of the new features I've go ahead and added. I am actually going to be starting the Kaggle competition, as I just mentioned a second ago. But I gotta be honest, work with me because I'm working with a few different technologies today that are fairly new to me, or I haven't done these things live. But I figured that people will want to see, since I'm working on the data science tutorial, maybe see some in-person live engineering and data science type stuff. So I'm doing this Kaggle competition right now. So I'm gonna go ahead and switch over to that. As you can see from the tabs, I have my Twitter open just cause, so I can actually, as a matter of fact, I want to share this stream. And before I get started, I actually wanted to test some music I have to see how it kind of sounds. So let's go ahead and get started. If you can hear it in the background, I just want to test and see how it sounds on the actual live stream. So just give me a quick second. See if the music is playing. And before I get started, I actually wanted to test some music I have to see how it kind of sounds. So let's go ahead and get started. Here in the background. Make it a little louder. I'm just testing it. Quick second. It sounds interesting. I'm trying to. It sounds a little low, right? I'm making it a little louder. I want it to be. It sounds good, right? Yeah, that's good. Okay, so, all right, let's go ahead and get started. I actually plan on doing a lot more of these because I figure why not? So, all right, let's go ahead and get started. All right, music sounds good. Yeah. Okay. All right, so let's go ahead and get started. So I'm gonna take my time because we're gonna be doing some coding live. So let's talk about this competition first. Now, this is not a paid for. This isn't any prize money involved in this. Actually, I'm part of a team, but we're gonna be submitting this. But things are, well, first of all, let me open to the actual competition. So this is one of these tabular playground competitions that Kaggle hosts. These are really for entry-level people who want to do some data science stuff. And you know, who are really interested but don't, you know, obviously don't have as much. So this is a May edition. It might be monthly. All right, so I'm just gonna talk about this playground series a little bit. Kaggle competitions are incredibly fun and rewarding, but they can also be intimidating for people who are relatively new in their data science journey. In the past, we've launched many playground competitions that are approachable. Basically, playground competitions are I think you may get ranked, but it's, you know, like quick match, but for Kaggle. Goal of these competitions is to provide a fun and approachable for anyone tabular data set to model. These competitions are a great choice for people looking for something in between the Titanic getting started competition and the feature competition. Feature competition, which is one I'm actually working on as well. That is the JPX Tokyo Stock Exchange. Now that one I'm not going to be live streaming because that's when the actual competition. I really don't want to give away what we're going to be using. But in these tabular playground series, I mean, you could just kind of play around with these with some machine learning to get you kind of started and just kind of go from there. Just experimenting, right? So the data, I believe the data is something simple. I think it's like manufacturer. For this challenge, you're giving simulated manufacturing control data and are tasked to predict whether the machine is in state 0 or state 1. The data has various feature interactions that may be important in determining a machine state. Good luck. So 0 or 1. So this is gonna be a binary. Because there's only two classes: class 0, class 1. So how they want you to do is they want you to actually have your column, which has their ID number and their target. What exactly is their target? Schools normalize, so it's training, testing. Okay. Also, before I read it, I want to get this started. This is the notebook that, you know, I started. Well, we started, me and someone else. It's actually, what it does is, I mean, kind of big on the EDA. Which is the exploratory data analysis. You're normalizing data, seeing how it's distributed, etc., etc. There's some PCA, we're clustering, and there's some TSNE clustering that we're not really using because it's too computationally intensive. Then I got a regression model against this for prediction. It's gonna take a little minute to run, maybe like 25 minutes to run. So I'm gonna go ahead and run this first, and as it's going, I'm going to go ahead and just explain it. So yeah, so let's run all. I'm using Colab for those who are new. People either use Colab or Jupyter Notebook. For Kaggle competitions, I kind of like using Colab a little better because it has TensorFlow already built into it. All you gotta do is just import it. I'll show you that in a second. So let's just run everything really quick. Okay. Now I'm connecting my Google Drive. Another good thing about Colab is, you know, you can pretty much build, what's a necessity, that you can pretty much build your Colab into Google Drive, so you can simply just you know, import the little statement, and pretty much just access Google Drive from your your Colab. your collab notebook. So as it's going through, I'm just going down cell by cell. So first, we're importing Numpy and Pandas. We're gonna be zip some files, so we're gonna be importing that. We're gonna use sklearn and some of the tools for that. We're gonna be scaling the data using the z-score, reporting PSA and tsne, which we probably won't be using. We're gonna import matplotlib to plot our visuals and seaboard. It's interesting because we made some functions that perform EDA and actually create an HTML report. And it has two different functions. I'm actually not super familiar with these. I'll try to ask my team member about these a little later, but these are just, as he explained to me, these are just exploratory data analysis functions. Yep. Okay. So we got our training set, test set, and our sample submissions. The good thing is Kaggle actually provides a sample set submission file for the correct format. Now we start getting into importing our Google Colab architecture. We're importing our files for our training test and our sample submission. And we are setting them to the data frame using Pandas right here. So PD is Pandas. This will make a lot more sense when my Pandas video actually comes out, but you're actually splitting the data set, which is interesting. The thing about it's interesting to me, I didn't understand why we need to have both a training and a test CSV, because really I'm going to be making the test data frame or the test set from the training set. So I don't know, maybe that's just extra for beginners so they know. So this is our training data set. I think this is just the info. So these are all the fields. They're basically pretty standard fields. Nothing special except the ID. Same thing with the test. Only thing is different between test and training. Training actually has the target field column. Okay. So first, and this is all explored. We're still in the EDA phase. We're checking for missing values, null values. For us, there are none in our training set. And yeah, when it says df is null.sum, you're just adding them up. You get the total amount. As you see, there's nothing but zeros. All right, now we're describing our training set. You can see when you do describe.t, it gives various stats: the mean, standard deviation, and minimum value. Bottom 20%, 50%, 75%, and the highest value for each field. Same thing with the test. Okay, so now we're setting up our categorical values. As you can see, I mean, it's pretty standard. For every kernel in our training data set, we're going to have a kernel COL. Okay, they just declared that. So kernel name is whatever the string is. The data type is whatever the data type is. It's going to check for the objects, the float type or integer type, and it's going to print it. Now we have our columns. As you can see, our columns right here. And this would be the target right here. This is the prediction. Same thing with test. Same thing. It's all gonna be similar. So now we check for any duplicate rows. There aren't any. Now we start getting into the PCA. Anybody knows about the PCA? This is principal component analysis. When you're doing this, you're basically separating your data points into clusters. And you're doing that so you can better find a variation between data points. You want to do this so it makes it easier to run your prediction algorithms. You essentially want to define the number of principal components. Principal components are essentially the most significant data point clusters, and they form their own components. Right? So we want to find a principal component and a percentage of the variance. As you can see, is a bunch of floats. Next, we want to visualize the explain individual components. As you can see, the curve is I mean, it is a curve that's actually positive. It's a positive curve, and you can see it's just pretty much the number of components we have as we see. The higher the explained variance. So it reaches its peak at 30. Right? So next we want to find the least known components, and that can explain a good 70% variance. So basically you're trying to find the number of components that can explain 90% of the variance, and you do that because you once you have 90% of variance, you can pretty much go from there. Let's see. Got a color palette. I believe that. Okay, greater than 25% is blue of explained variance, and less than 25% is the pink. So the blues are the values that we want. You can see that the reds are pretty much negatives for all of them. So you want to have greater variance between your components. Okay, now this is a part where we start getting into the plots. See, we formed a little scatter plot that shows the decision boundaries. I'm gonna do another decision boundary. Well, it doesn't show a decision boundary, but it definitely shows the clustering. All right. We have a little confusion matrix. There's a lot of different. Not a huge fan of these types of confusion matrix, but because they're hard to read. But essentially, we have a bunch of different fields, and it's doing the true false, true false, true false, or true positive, false positive. True negatives is getting the, well, this one in particular, usually I have, it's called a train test split, or train test split. It's a function that's built into Python that gets you a better looking confusion matrix, because it also prints out all the precision, accuracy, recall, F1 score, etc., etc. I would have done that better. That's me, but I didn't do that, honestly. Okay, so now we're gonna do a little gradient boosting. there's this gradient boosting method that's called light GBM. Gradient boosting is essentially a form of feature optimization. Essentially, you're finding a feature that's the most significant, or let's say the feature that's most significant, and you're looking at what it will be at its most significant, and when will it have its most impact. Right? That's essentially what gradient boost does. Gradient boost is a very powerful machine learning algorithm method. It's very useful. I was actually just reading that like most of the winners who win their Kaggle competitions use gradient boosting. So as you can see, once we define the input and output, train test. Oh, well, here's train test split. I like using it because it's it pretty much you can use the original data to fit it on to either a testing set or a validation set of your data, and pretty much just go from there. We kind of the curves. You can see this is essentially a curve I was showing you earlier, except these numbers right here are each individual. Hold on. Let me make sure I know this before I say something crazy. Fit train. Okay, so these are the level of importance, right? So the reason that they're plotting the level of importance, as you can see, once we get to 300 features, it's still going up. So the more features it has, ironically enough, the higher the importance, which makes sense. The more features it's going to have, the more important it's going to be. And the curve still looks the same, pretty much, right? And this must be the loss. Yeah, this is a loss. Okay, so, and this is a number of iterations. As you can see, it just pretty much flattens out at 200. So that's actually decent. Number of error loss. So more error loss, the worse your prediction is. So you want to have a lower error loss. And right now our error loss is at about 0.45 when we get to 200 iterations. So, see, this is a confusion matrix that it's a little easier to read. You know, you have the 0, 1, 1, 0 for your classes, and you could pretty much just go and easily identify your true positives, true negatives, etc. And look at the distribution, at least for the predicted. This is still predicted. Okay. Now we have model features based on average over folds. Again, F26 seems to have the highest value level of importance. It's interesting because right now we have a weighted accuracy of 0.82, which, I mean, I prefer, man, I'd really try to get in that 95%, you know, that 95 percentile of prediction accuracy. So sometimes it's not possible though. Sometimes it's just not possible. You know, you deal with that. No data science project is the same. So, all right. So this is why I like Colab over Jupyter Notebook, because I like being able to just import TensorFlow easily without having to install the environment and everything. It's not really difficult to do in the Jupyter Navigator, but with Colab I could just, you know, get started. and I think it's a little more user friendly. So that's what I'm pretty much importing here. All my TensorFlow, Keras, optimizer. Actually, I'm using TensorFlow, Keras, but I'm actually going to do one model with PyTorch. I see a lot more people using Keras over PyTorch, but I also see a good deal of PyTorch out there, so I think it's good to learn both. Okay, and these are going to be used for neural networks, regression, classification. So I'm more and more Keras, more import statements. Okay, so, and I'm going to start actually kind of getting rid of those. I get rid of a lot of these comments tomorrow because I'm going to submit it probably tomorrow, but I'm going to be working on it tonight. Yeah, okay, so sometimes you'll find that you'll have to drop different columns because they're not that significant. The reason I drop ID, because ID has no significance on the value. It's just the number in the field. So it's not really necessary. So I'm actually dropping that. You can drop that just simply by having your data frame and then doing dot drop, and you do whatever column. And since we're going based off the columns, you do access 1. If it was the rows, it would be access 0, right? So after you drop it, pretty much get all these fields, but you just don't have the ID field anymore, right? So our shape is 700,000 by 31. So there are 31 fields and 700,000 data points, right? Some of this stuff's gonna look a little funny because I was working on it, but you know, I'm gonna be cleaning it up tonight and also experimenting with a couple of different machine learning models. Okay. Basically, in this one, I'm doing the same thing like I was doing before, just replacing any null values with a 0, right? Or replace null values, which is non, this right here, in each column with the median value of that column. Yeah, which is unnecessary because there aren't any null values. And again, we just kind of going through the motions. Okay, so like that. Right here is, see, what I did was I essentially dropped the target as well. I think. Yeah. Okay, so I dropped the target. We're going to be splitting the testing and data set. And the testing set is going to be 10%. That's what this is, 10% of the actual training set. And we're going to create a validation set. So a validation set is going to be 3% of the entire training set. So you can see it right here. It's you know, number of labels doesn't change, but the number of samples does. So 785,000, 24,300 in the validation set, and 90,000 in the testing set. And the reason you have to do this, before I even go forward, you gotta learn this. This is very important. Your training, testing, and validation, you never want to perform predictions on your training set. No, you never want to perform predictions on your testing set. You only want to test your predictions on your testing set. You want to perform the modeling on your training set. Use the validation set against your training set, and then use the training set against the validation set, essentially. So the training set is your initial data. The validation set is used to test your training data against a smaller set, and then the testing set is used to predict what it will be against the testing set is used to predict. I'm sorry. The training set is used to train. You fit and train your model on your training set. The testing set is what you predict your training against. There it is. And the validation is how you test against the training set. Okay, so in this we have two different classes, 0 and 1. You can see it's pretty much even. It's pretty close. So I don't think you need to use the weighted accuracy in this instance, because you can see the lines are pretty close. You really only use the weighted accuracy when the imbalance is like really ridiculous. It'd be like this bar is up here and then this bar is like it ends up here. Then you're like, okay, I need to use a weighted accuracy. Okay, so now we're going to be applying feature normalization to the training, validation, test sets. We're using the min-max scaler, so we're taking the minimum value and the max value for scaling. We're going to be training it on the training set. We're going to transform it, and we're going to transform wow, really. And then, okay, so this is where we start getting into the modeling. This is when we start getting into, right now I'm doing a logistics regression model. I'm doing this to compare, because we have two classes, 0 and 1. I'm going to be comparing classes. There's so many ways to do this, but this way I did. Okay, so this is what I was explaining earlier. So you train your two initial training, and your X training and your Y training. Y training being your labels, X training being your data sets on your logistic regression model. Then for prediction, we're going to predict against the validation set. And the reason we're doing this, because this is regression, not classification. Okay, we are comparing stuff. We're not classifying anything. So we're going to be predicting on a validation set. Then we're going to create a confusion value based off the Y value, which is the labels predicted, and the actual label prediction. So these are the actual labels. These are the predicted labels. Okay, next we got to do one-hot encoding. One-hot encoding saves us a lot of time, honestly. But one-hot encoding essentially says, here data point, you're going to go to this particular neuron, and we're going to artificially give you 10 labels in this case. We're basically going to force you into one of 10 different labels instead of the 31 that we had initially. Okay, so now you can see our new dating set is 785 700 by 10. Right? Okay, so now we're actually doing our classifier, right? So we're actually, the thing about when you see these x equals mp.zeros, you're actually artificially creating a bunch of zeros with 100 data points and one label, right? For your x value and your y value. X is always going to be data points or samples, and y is always going to be labeled. In this case, little x, I had to do the same thing. I had to drop the target variable again, or target column again. And we're going to be actually randomly selecting a Gaussian normalized component, either the first class or the second class, with a probability of 0.5. That's 50%. This is going to be a uniform random distribution, similar to a forest. And if r is equal to 0, I know I know some people are not gonna understand this, but I just really kind of would get down. I'm kind of, believe it or not, I'm doing this myself while I'm going through it with you all and teaching you all, and also making it right for this competition. Okay. So basically gonna be just pumping a bunch of random variables. Okay, now you can see the distribution. Y is equivalent to 0, which is the first one. So, okay, so this distribution is basically our new distribution of our samples and the new labels. So, blue. So, blue, you see where it says X, Y is equivalent to 0. The Tim Ben's color is blue, right? You can see blue being 0, being the class 0, takes up more than 1. There are more blues than 1, or at least it's more significant than 1, right? And this one is interesting because we're actually going by the mu, which is obviously the mean, the sigma, which is the standard deviation, which we're actually trying to get the scores of each class. So mu for class 0 is going to be 2.288, which is the mean, and the standard deviation is 1.019. For this class 1 is 6.10, and for class 1, wait a second, this should be 0, 0. Okay, yeah. Okay, so yeah. Okay, it's gonna be, for standard deviation for class 1, it's gonna be 0.45. Okay. Now, this is when we start getting into the probability distribution functions, and eventually you're going to see the decision boundary, which should be somewhere around here where they actually cross. The two plots you see are actually this may be the MAE. No. Dictionary. Function. Okay, so this is probability distribution function of the two classes. The skinnier it is, the more significant it is. Which makes sense. Okay, so I think blue is also class 0 again. X, P1, P2, X being... Yeah, blue is class 1, red is class, or blue is class 0, red is class 1. Okay. Yeah, I didn't like this this fit. It says 1.0, but I'm not sure if it might be due to overfitting. But this is actually a regression model, and you're actually getting the fit of the first 90. Yes, yeah, I was going to say bottom 90%, but no, it's just the first 90 data points. The fit's 100%. Same thing again, you get on a remaining 10. It says 100%. You know. Now, you see our decision boundary? You know, that's exactly where the two probability distribution functions actually cross, and the decision is actually made. You can see this with this green line right here, right? All right, so that's the logistics regression model. Now we're going to start getting into the neural networks. Now, I created for this one a multi-layer perceptron model, and as you can see, I only added a few layers. With MLPs, you can pretty much add or subtract hidden layers to experiment and see how you get a better prediction accuracy. Matter of fact, all right, so I'm glad I ran that earlier because I'm glad everything finished by the time I got down here. What I'm thinking about doing is maybe either another MLP. Oh, I'm getting distracted. Let me finish going through everything first before I start kind of getting into my experiments. But okay, so what we're doing is we're using Keras and we're creating a neural network, right? The neural network will be sequential. It will have initially 128 units, have a ReLU activation, which is, you know what? Let me let Wikipedia explain ReLU activation, because you probably do it better than me. It stands for Rectified Linear Unit. I believe, before I even read it, I believe it replaces when it's not the value. I think it's this 1 and it pushes it through. I forget. Let me read it. Okay, or when it's 0. Okay, well, anyways, in the context of artificial neural networks, the rectifier, or the ReLU, Rectified Linear Unit Activation Function, is an activation function defined as a positive part of its arguments. Fx equals x plus, which means the positive samples. Prediction accuracy equals max 0x, where x is the input to a neuron. This is also known as a ramp function and is analogous to half-wave rectification in electrical engineering. Okay, layer RU, that's strong biological. Linear unit, fine application, computer vision, and speech recognition using deep neural networks and computational neuroscience. Okay, because this is also gradient. Maybe I can get it. Maybe I can get a better, more human explanation. Okay, here's a better one. The rectified linear activation function, or ReLU for short, is a piecewise linear function that will output the input directly if it's positive. Otherwise, it will output 0. So, okay, so this makes sense. Okay, if it's a positive number, i.e., if there's a positive correlation between two data points in a neural network, the ReLU will push it forward. If it's anything other than positive, it will push out to 0. That way, when it gets to the next layer of the hidden layer of the next neuron in the hidden layer, it doesn't need to worry about those values that were 0 because it already knows. Because there was if they were less than 0, then ReLU just makes them 0. Then it already knows that it doesn't need to check for those, so that way it speeds up and gets more accurate as it goes through each iteration, because it doesn't need to look at the previous ones. All right, so we're gonna do a ReLU activation. There's another layer I'm adding of 128 units. We're going to do a dropout layer, and the dropout layer, what the dropout layer does is it removes a certain percentage of data samples. I said that to take 10% every time it goes through an iteration, remove or every time it goes to each node in the layer, remove 10% of the variables to prevent overfitting. Overfitting is essentially your stuff is too complicated and you're giving it unnecessary values. So then I add another layer, 256, just cause 256 units. And then finally I get my output layer of 10. So we're gonna have 10 labels. And it's going to be a softmax activation, which means it can be 0 or 1. Is that softmax or sigmoid voice? Sigmoid. Sigmoid versus softmax. Yeah. Sometimes I got to do these a few times just to keep this fresh in my head that, like, yeah, I don't remember everything. But the more I keep looking at it, the more I start to get it back. Okay, yeah. So we're using softmax function, which is used for multi-class logistic regression. We have 10 different classes, so we're going to be using softmax, right? Adding a callback just in case it starts losing its accuracy or accuracy isn't going up. And for this, I think the highest accuracy for our MLP model was 78.78. Which obviously isn't great. You can kind of plot the training versus validation. You know, we need to do a little bit better than that, right? Our accuracy, exactly. Our mean accuracy. And our loss was 0.46. That's not that great, right? So we actually have the loss on the test set, which is 0.46. Hey, same thing. And yeah, so that's pretty much where we're at right now. What I want to do, I can do this a number of different ways, and I've been writing down some notes. Let me see if I can find some down, because it's good to kind of write this stuff down too. So I'm really doing data science. I mean, there's a couple of different things I can do. Right now, we just have this MLP. What I'm thinking about doing is adding a couple, or experimenting with a couple more models. I'm thinking of maybe a XGB, which is a gradient booster. Is it extreme gradient boosting? Something like that. XGB is very popular gradient boosting algorithm method. The classification. I'm thinking about using a KNN. I think about using a KNN classifier, which is a nearest network. K nearest network, yeah. Classifier with XGB boosted. I think that we might get some better results from that. Because right now, 78% ain't that great. We want something a little bit better. Oh, I wrote down some notes about ReLU. ReLU works by maintaining only positive elements, and by taking the maximum of that element and zero. Since the input is negative, the derivative of rel u is 0. If the input is positive, then the rel u is 1. It's by mathematical induction, MLP is a piecewise linear function of the output. So yeah, write down some notes. I hate using pens. All right. So far, what have we used? We've used PCA. We haven't used TSNE because it's too slow. We've used a logistic regression algorithm for regression. And we've used a MLP model for classification. And yeah, all right, so we've used PCA, we've used MLP with 5 layers. What else? Did I say? LR model. Regression. For classification. We're not, I mean, this is 0.7. We're only, yeah. So again, I like to say, if I could get to anything above 0.95, I'm cooking with oil. Sometimes I'm not that lucky. But you have to do as many tests and experiments as possible. Again, this is a project I only started probably about a week and a half ago, and this is due today. So it's not like, this needs to be perfect. It's just something that we could submit just to say we did, just for a little bit of practice. Okay. So right now, I have just a logistics and regression model. And the good thing, and this is when it starts to get fun, I have so many other machine learning models that I've created myself or that I've used that I can pretty much just throw so many different models at our data, our training, just to kind of, gauge it. There should be a specific, I mean, you can't just have 1,000 different models because it needs to be able to save on computational power. It needs to be efficient. And it needs to, it can't take, 2 hours to run. I think there are actually some rules into how long it takes to run. You split a maximum 5 entries per day, or up to 2, or you may select up to 2 submissions to final judging. I'm only gonna have 1 for final judging. I'm looking to see how long, because Kaggle usually gives you a specific time limit on how long it takes to actually run your data. May select 2 meshes. Innovative automatic suitable. Your final score may not be based on the same exact subset of data as a public letter 4, but rather a different private data subset of your full submission. Your public score is only a rough indication of what your final score is. You should thus choose submissions that will likely be best overall and not necessarily on the public subset. That makes sense. UTC. I think they might not have. I know on the one with like the one that's worth money, there's like a time limit where it's like it can't take more than a specific amount of hours to run. So there might not be one on this, but also the data set isn't nearly as big. But you never know. Okay, so that's fine. Okay, so this is where we pretty much left off of this. I don't necessarily want to start this late at night because this was just a first kind of experiment, kind of test run of this. I really want to see how popular it's gonna get, if at all. I'm probably still gonna do it, but what I want to do, because we're gonna be having weekly meetings every Sunday to go over a lot of this stuff, and this will be the team. We'll have probably, what I'm thinking of is we'll have maybe a public one that we'll do for an hour, and then we'll maybe switch off to the private one with just the team members. After that, so we're using a Discord server right now for coordination and all that good stuff. But like I said, I think tomorrow I'm just gonna, depending on how long it takes, because again, this is, well, tomorrow, I can't say tomorrow because it's actually, late at night here, but I believe that more than likely later today, May 31st, I'm gonna try maybe one more regression and classifier and maybe another neural network and see if I can get maybe 4 or 5 working models before I do the final submission. And then I'm going to be testing these things throughout the day. So, this is just for fun. It's not going to be too too ridiculous. So yeah. So thank you so much. Thank you so much for paying attention. I definitely enjoy doing this type of stuff. It's definitely something that I think it could be beneficial to a lot of different people. But for me personally, I get to teach people who are very interested. I get to compete, which I'm very competitive as a person, people who know me. And I also get to learn some new things myself, which is always going to be great. I want more people to, if you're not gonna participate, at least you could stop by the YouTube channel, drop a like, share, and go ahead and subscribe, because I think I'm gonna be doing a lot more of these going forward. It's pretty much like, yeah, why not? Like why? Oh, I didn't even open the chat. I told you how. I was doing so much pre-work before I did this that I didn't even open up the chat. I didn't expect too many people to be on. It's super late, but Yeah, thanks a lot, engineering fam. We're definitely going to be doing more of these. Stay tuned. Drop a like. If you have any questions, especially about any of the stuff that I went over today, please. I know some high level stuff, but it's not that bad once you get into it. And I guarantee you will be hugely beneficial. So with that being said, engineering fam, this was an episode of Get on Code Kaggle Competition live. I appreciate anything and all the support. That's it.